Section 1.4, the matrix equation. In this section, we will focus our attention on three forms of the same system. One is vector equation form, which we have seen in our previous class 1.3. And here we'll also look at matrix equation and augmented matrix form. Okay, so for the given system, we can write the given system in different form: vector equation form, matrix equation form, and augmented matrix form. All right. So, for example, example 1, consider the system. Now, how do we write this given system in vector equation form? What is that vector equation form actually means? Okay, let us see this. So in vector equation form, so x1, and we have a vector plus x2, write a vector there, plus x3, write a vector there, equals this way. Okay, so in vector equation form, x1, we have a coefficient of x1 in the first equation as 1 and -5. And the second one is for x2, the coefficient is 2. Oh, sorry, this one is 1 and 0. Okay, there is no x1, so this is 0x1. So this is 1x1, here 0x1 in the second one. So 1 and 0. x2, this is 2 and -5. x3 is -1 and 3. And the constant term is 4 and 1. This form is called vector equation form. So that means this equation, system of equation, can be represented as vector equation form in this way. Now, how can we write matrix equation form? Okay, so matrix equation form is AX equals B form. Okay, B means always the constant part. We consider this constant term as B. So we write this in the form of AX equals B. So A represent where A is the coefficient matrix. Coefficient matrix, and X represent x1, x2, x3 in this case. So what it means is your A is 1, 2, -1, and 0, -5, 3, that is my coefficient A. Okay, all the coefficient, and then X, AX. So X is x1, x2, x3, and B means the constant term 4 and 1. Notice that this is your A, matrix A, this is your X, and this is your B. All right, A, X, B. So this is called matrix equation form. And C, augmented matrix. So you already know what is augmented matrix is. So augmented matrix will be 1, 2, -1, 0, -5, 3, and 4 and 1. All right, so they all have the same solution. In another word, if we are given a system of equation like this, you can write this in the form of vector equation, or in the form of matrix equation, or in augmented matrix form. So sometimes some method, some form will be easy to deal with. So you should know, all these, given system can be expressed in different form. So whatever form you find easy in order to deal with for that particular situation, then go for it. They represent the same thing. They will have the same solution set. So let's look at example 2 quickly. For the vector v1, v2, v3 in Rm, write the linear combination as a matrix times a vector. Right? So this is the given linear combination, and we want to write matrix times vector. All right? So the vector here will be, matrix will be, the matrix represent v1, v2, v3 will be the matrix, and then the vector will be 3, -5, and 7. So if you multiply these two matrices, you're going to get this, right? So it's that simple. So this is in the form of AX form, matrix times vector. All right. So Theorem 4, I just want you to read this, and this may be helpful to solve problems later on. What this theorem tells us is that let A be an m by n matrix, then the following statements are logically equivalent. What it means is if one statement is true, all of them are true. If one statement is false, then all of them are false, okay? So for each B in Rm, okay, B is a vector in Rm, the equation Ax equals B has a solution. So if it has a solution, then each B in Rm is a linear combination of the column of A. So remember that A is a matrix. So B is a, linear combination of the column of A. In another word, B can be written as a span of column of A. Okay. So the column of A span Rn. And A has a pivot position in every row. So these are either, if one is true, all of the others are true. If one is false, all of the others are false. Example 3. Compute AX, where A is given this matrix and X is given there. So if you want to compute this AX, you can write this as 2, 3, 4, -1, 5, -3, 6, -2, 8, and then x1, x2, x3. So as you know from chapter 2 that we have done earlier, so this is 3 by 3 matrix and this is 3 by 1 matrix. So since the column of the first row and the row of the second matrix are equal, so the result, the multiplication exists, and the resulting matrix will be of the size 3 by 1. So let us multiply that. So you already know how to multiply from chapter 2. So if you multiply that, so you're going to get 2x1. So consider the row with column, okay? Multiply each of these entry of row with the column. So 2x1 plus 3x2 plus 4x3. And now consider the second row and multiply with the column. So that means -x1 plus 5x2 minus 3x3. And then the last one is 6x1 minus 2x2 plus 8x3. So when you multiply, this is what you get. Okay, Theorem 5. If A is an m by n matrix, U and V are vectors in Rn, and C is a scalar, then AU plus V equals AU plus AV. ACU can equals CAU. Okay. Let's look at one example, example 5. So what that theorem actually means, we'll prove that theorem using this example, okay? We are given a matrix A and vector U and V. U and V are vectors because it's, remember how we define is that it's, so by definition, it represents the, direction and the magnitude and length, distance. But we already said before that whenever we have one column matrix, we call it vector. So this is one column matrix. It's a vector. So this vector is in R2 because there are two entry. Okay, both of these vectors are in R2. All right, so verify theorem 5a in this case by computing. Okay, let us compute A U plus V. A is 2, 5, 3, and 1, and then U plus V. So U is 4, negative 1, plus V is negative 3 and 5. This gives me 2, 5, 3, and 1. And then you're going to get 4 minus 3 is 1 and negative 4. So if you multiply this, then what do you get? (22) 2 times 1. Sorry, this one is 1 and 4, not negative 4, 1 and 4. So you're going to get 22 and 7 when you multiply it. And let us calculate AU. A is 2, 5, 3, and 1. U is 4 and negative 1. If you multiply that, so you're going to get 3 and 11. And AV is 2, 5, 3, 1. And V is negative 3 and 5. So if you multiply that, you're going to get 19 and negative 4. And so we have AU plus AV equals 311 plus 19 and negative 4. That's going to give me 22 and 7. So notice that they are equal. So therefore, we can say that U plus V, A times U plus V equals AU plus AV. Okay, we proved that first condition. Now, okay, that's the only thing we want to prove here, so we are done. Okay, last questions for this section, example 4. So we are given a matrix A and vector P and vector B. And it can be shown that P is a solution of AX equals B. Use this fact to exhibit B as a specific combination of the column of A. I will divide this question into two parts. Okay, so in part 1, the question is so that P is the solution of the system AX equals B. That's one question. That's one part. And the second part is write B as a linear combination of column of A. So write B, vector B, as a linear combination of column of A. All right, these two questions. So first thing first, let us prove that P is the solution of AX equals B. So if P is the solution, that means P is the, P is X. So whatever the x value is, that is the solution, right? So for any equation, any system here, so if solution means the x value, so that means if p is the solution, then we have to show that x and p are equal. Okay, so first thing to show p is the solution of ax equals b, we need to show that x equals p. In another word, we need to show that AP equals b. That's what we need to show, because ax equals b means x and p are equal. So the value of x is p. So that's the solution, right? So let us check what is AP. So A is, let me just copy that, 1, 5, -2, 0, -3, 1, 9, -5, 4, -8, -1, and 7. And P is 3, -2, 0, and 4. So notice that this matrix A is 3 by 4, and matrix P is 4 by 1. So then the matrix multiplication exists, and the resulting matrix must be of the size 3 by 1. So let us multiply that. So if you multiply, I leave it to you. I think you know how to multiply it. I'll give you a couple of minutes. Please multiply and let me know. You already know from chapter 2, from previous class, how to multiply. So if you multiply, you should be getting -7, 9, and 0. So yes, it proves that this is actually B. So P is the solution of AX equals B. All right, because this is B. Now part B, we need to write B as a linear combination of column of A. So how we can write this as, let us consider the matrix equation here. So consider matrix equation, which is, matrix equation means AX equals B form. Let me write that. So 1, 5, -2, 0, -3, 1, 9, and -5, 4, -8, -1, 7. And X, P is the solution. Then now we can write AP, because we already proved that P is the solution. Let me write P there. So 3, -2, 0, and 4 equals B. So B is -7, 9, and 0. Now this is a matrix equation. Now we want to write this in vector equation. That is what the linear combination is. Okay, because vector equation means, suppose x1 a1 plus x2 a2 plus, that is the linear, B is the linear combination of this, and this form actually is the vector equation form. So in another word, to express this as a linear combination, we just write the vector equation form. Okay, so the vector equation, and we have already seen how to change the given system into matrix equation form, vector equation form, and augmented matrix form, and they represent the same thing. So the same thing, we will write this as a vector equation form. This, convert it into vector equation form. Equivalent to a vector equation form as, so that will be, notice that in this case the columns A1, A2, they are column here, as you can see here from this one. So x1, this is your x, so this is your x1, x2, x3, and they are the column A1, A2, A3, A4. So they are the column of matrix A. So how we write is x1 means 3. Notice that I will write x1 A1 plus x2 A2 plus x3 A3 plus x4 A4 equals B. So this is the linear combination, or you can say vector equation form, same thing. Okay, so x1 is 3, A1 is 1, -3, 4, plus x2 is -2. Let me just write -2 there, and A2 is 5, 1, -8, plus x3, which is 0, and A3 is -2, 9, -1, plus x4. x4 is 4, and A4 is 0, -5, 7, equals B is -7, 9, and 0. All right, so we express that in matrix equation form, and then we also express that in a linear combination. And I mean, we express B as a linear combination of the column of A. Okay. All right, this section 1.4 is done.